this assessment asks us to predict the product of the syn dihydroxylation, paying careful attention to the stereochemical issues. Now, as a planar alkene, this osmium tetroxide can approach from the front or from the back, and in fact, both are going to happen at an equal rate. Spoiler alert, we're going to get a racemic mixture. But when it adds, let's look at the example where it's adding from the front. When it adds, it's going to do so in a concerted mechanism, where these pi electrons attack oxygen, these electrons go on to osmium, that's how osmium gets reduced in the process, and these electrons go here in what we would consider a 6-electron cyclic transition state, one that we'll see quite often going forward. Well, if we look at that, given that it's concerted, both bonds to oxygen are going to form at the same time before we have a chance to rotate around this pi/sigma bond as it moves from pi to sigma in the reaction. That gives us the following product. We're going to keep this portion in the plane. We'll show our 2 new bonds to oxygen being bold wedges. We make this osmate ester. We can show the ethyl group back and the hydrogen back. Now we illustrate this just to reiterate that both bonds are forming on the top face in this concerted step. Now, in truth, half the time it's going to approach from the back, so we would get the enantiomer of this. Step 2 is a reaction whose mechanism is somewhat complicated, so we won't show it, but this oxygen-osmium bond, both oxygen-osmium bonds are going to be cleaved and replaced with a proton, so that the product we would draw in the end is this syn-diol. We'll draw on the hydrogens just to be consistent, and so we end up with that product. But not just that product, we're also going to end up with the enantiomer of that product, and so we can show the other one where the hydroxyl group is down, both hydroxyl groups are down, the hydrogen is up, and the ethyl group is up. So both of these would be present in a 50-50 racemic mixture.